From a handful of simple rules, something unexpected can take shape. A bug swarm that moves is one, a school of fish swimming in sync, a herd of sheep rolling across a field, or a flock of birds or bats weaving through the sky. That's the beauty of emergent behaviors. You can get some interesting and complex systems arising from just a few simple interactions. In this episode of the Codex, we're diving into how that works, not in nature, but inside a computer simulation. We'll look at a flocking simulation built in Godot, powered entirely by a compute shader. Thousands of agents, each following just a few basic roles where the GPU handles all of the heavy lifting. Along the way, we'll see how three small forces, alignment, cohesion, and separation, combine into the illusion of collective intelligence, known as Boids. You can grab the full open source project on GitHub if you want to try it yourself. Let's get started. The word Boid comes from the phrase birdoid object, meaning bird-like object. It was coined by Craig Reynolds back in 1986 when he created the original Boids Simulation, a landmark computer model showing how flocking, schooling, and herding behaviors can emerge from simple local rules. Each Boid follows three simple rules: separation, alignment, and cohesion. And together, these rules create a realistic flocking behavior that almost feels alive, but has no central control. You might think there's a hidden brain controlling the flock as a single entity, but there isn't. Each Boid is acting on its own, yet together they feel coordinated. We'll look at those three forces in a few minutes. Alright, so now we know the core idea behind Boids, but how do we actually make it run? Let's look under the hood and see how it works inside Godot's Compute Shader pipeline. In GDScript, we'll use Godot's rendering server and rendering device features to set up and run the compute shader sequence every frame. It calls into the compute pipeline 3 times each frame, each handling one stage of the update, clear, draw loop. The results are written directly into a GPU texture, which is then displayed inside a texture rect node at the end of the frame. Each Boid is just a simple set of values, a position vector and a velocity vector, both stored in GPU buffers. We'll have both an input and an output copy of these values, so we can swap the data after each frame is finished. At startup, the script randomizes their positions, sets up the rendering pipeline, and prepares the uniforms and buffers for the GPU. Then, every frame, it sends the position and velocity buffers and a bunch of configuration parameters into the GPU. Things like the delta time, the vision radius, some steering weights, and speed limits and draw radius. The Boid's positions and velocity arrays are sent in using GPU buffers. All of the parameters are sent in through push constants, so we can tweak those as the sim runs in real time. And we'll also provide the shader with an output image to draw into. This RGB image is what is displayed in the Godot scene after each frame is finished. Now comes the fun part. The GPU takes over and handles the current frame's data. Each frame runs 3 quick compute passes in sequence: simulate, clear, then draw. The sim phase, where it runs the main flocking logic for each Boid in the input buffers, the clear phase, where it wipes the previous frame's image buffer, and the draw phase, where it renders each Boid into a fresh image buffer. During the sim phase, each Boid scans through all other Boids and reacts to any neighbors within its vision radius. For those neighbors within the radius, the shader needs to calculate a steering force. Each of the 3 main forces contributes a vector to the steering force, scaled by that force's weight setting. Adjusting those weights will change the flock's overall behavior, giving us tighter clusters, smoother arcs, or loose swarms. Once it has the final steering force for the frame, it updates the Boid's output velocity and its output position to be used in the next frame. It's doing this for many of the Boids all in parallel. That's the magic of GPU compute. Every agent runs the same small loop, usually in large batches, giving us reasonable performance even when working with tens of thousands of Boids. We could enhance this logic later if we wanted even better performance, but for today we're sticking with this brute force approach. Okay, let's break down the 3 force components in the Boid simulation. Separation pushes Boids apart when they get too close. Alignment nudges them to match their neighbor's average direction, and cohesion gently pulls them towards the group's center. Separation checks the nearby Boids within the vision radius. When another Boid gets too close, it pushes away with a strength that rises sharply the closer they are, following an inverse square falloff where the force gets stronger as the distance decreases. Alignment sums up the neighbor's velocities and averages them together, giving each Boid a direction that it wants to match. That's how they steer in sync. And Cohesion collects the wrapped positions of nearby Boids, finding their center, and pulls gently towards it, keeping the group together even across the world's edge. Each of these forces becomes a vector, scaled by its own weight, then combined into a single acceleration value for the Boid. Small changes to the weights completely reshape the flock, from tight swarms to smooth flowing motion. In this implementation, the Boid's vision is circular, meaning each Boid only reacts to neighbors within its circle radius. Some versions of Boids use a vision cone or other kernels instead of a circle, for a more natural look, but we'll keep it simple here. Okay, let's take the new acceleration value and move the Boid to its new location. Every frame, every Boid updates its velocity based on the new acceleration. That's the steering effect we got from the three forces. So we'll shift the Boid's position according to that new velocity. The time step, or dt, controls how much simulated time passes between frames. We'll use the forward Euler integration method to apply acceleration and update the position over that interval. A smaller dt gives smoother, more precise motion, like slowing time down. A larger dt makes everything move faster, with bigger jumps from frame to frame. That's the heartbeat of the simulation, velocity and position evolving together one tiny step at a time. In this version of Boids, to keep the motion unique and interesting, we also added a few more settings. First, we can cap the steering force so turning can be adjusted. Then here, we can enforce minimum and maximum speeds, so the Boid never freezes or accelerates without bound. And here we apply a damping value, a little drag, so velocity gradually settles down over time. All of these settings are passed in for every frame. You can tweak them live in GDScript, and they come in as push constants, so the flock reacts immediately. It's also worth mentioning how we're handling the edges of the simulation. The world itself wraps around, leaving one edge to reappear on the opposite side, and so the force calculations use a wrapped position. That keeps the interactions continuous across the border, so the flock behaves like one seamless group. With two more settings, we'll be able to control the overall acceleration scaling and add some randomness to make the motion feel a bit more organic. To add life to the flock, we included a movement randomness setting, adding tiny random nudges to each Boid's steering so no two behave exactly alike. It gives each Boid its own slightly different personality. And finally, there's the movement scaling setting, adjusting the overall strength of a Boid's acceleration. Higher values make the Boid respond more strongly to the computed acceleration, moving sharply along the intended path and increasing speed. Lower values weaken the acceleration, so the Boid drifts more gently, creating smoother, more relaxed motion and reducing speed. Together, these parameters let us fine-tune how mechanical or organic the flock looks. And now we'll turn our math results from the simulation phase into visual motion on the screen. In the clear phase, we simply reset the texture back to a dark background tone, ready for a fresh frame. We wipe out all the pixels one by one. Then, during the draw phase, each Boid is rendered as a filled triangle, oriented along its velocity vector. Instead of traditional fragment shading, we're rasterizing the triangles directly in the Compute Shader using a lightweight GPU-based software renderer. The draw radius controls the triangle size, so they stay visible even when zoomed out. The color of each Boid reflects its speed, using a jet-inspired color map, from blue for slow movers to red for the fastest ones. The camera position, zoom, and draw radius are also passed in as push constants, keeping everything interactive in real time. You can pan with the right mouse button and zoom with the scroll wheel. These controls don't change the simulation math, only how the flock is displayed in our viewport. They'll let you explore the image from different scales and positions. At the end of each frame, GDScript will grab the new image data from the GPU and display it into our texture rect node. It finishes up by swapping out the new Boid data with the old data, so it can proceed to start the next compute frame. Perfect, and we have a ton of controls and settings to play with. And that's my version of the Boids simulation, organic patterns born from just a handful of simple rules. Each triangle on the screen is following the same tiny algorithm, yet together they form behaviors that feel alive, purposeful, and even intelligent. It's a neat example of emergence, order from simplicity. If you want to try it out, the full project is open source on GitHub. Expect your GPU fans to be busy if you crank up those Boid counts. Please like, hype, and subscribe if you enjoyed the video. Thanks for watching the Pathfinder's Codex.